Okay, I will start now. First of all, welcome all to this to the new year, and Happy New Year to everybody. Welcome to our new season of webinars in 2024. We are very happy today to start this new season with a presentation from a very powerful team from Thornton Tomasetti, one of the major engineering company not just in the US, but they have offices worldwide in many earthquake-prone countries as well. And I will introduce the speakers in a minute, but before doing so, just an update. You are now familiar with the number of presentation and webinar that we have delivered so far from April 2022, and we will continue to deliver. You can find all of them, just a reminder that you can find all of them on our educational pages, and that you can download it and listen to them and at your leisure, and contact us if there is any additional materials that you would like to receive together with them or in relation to them. Before we start, I would just like to speak very briefly about the Japan 1st January 2024 Noto earthquakes. I'm sure it's a very sad way of, let's see if it continues. Yes, it's unfortunately a very sad way of starting the year with was an earthquake of magnitude 7.6 with 232 deaths and 21 missing and more than 1,000 people injured. It was the major earthquake that struck Japan since the 2011 Tohoku earthquake. And it affected quite strongly the Noto Peninsula with an uplift of 4 meters and a westward move of 1.3 meter with a shoreline moving outward of 250 meter. There was also a major tsunami warning with an evacuation of 62,000 people. Unfortunately, it appears that the first wave arrived to Suzu after just 1 minute, and this is much shorter time that the usually computed time of 3 minutes with a flooding of up to 4 meters. The earthquake inflicted damage to 276 schools and facilities. This is of direct relevance to our community because we are looking at, after the school infrastructures, and caused 20 cases of damage to important cultural assets, besides the level of widespread damage and destructions of many residential houses that you can see here. Interestingly, 39 schools in the Wajima area were converted to evacuation shelters, with plans to transfer the students from Wajima to near prefectures so as not to interrupt their education. And quite interestingly, some schools managed to resume education after the 15th of January, i.e. 2 weeks after the event. As you might have, as you know from our previous, some of this audience from our previous conversations. Why is that? We have done work on trying to minimize education disruptions. This was a project that we ran with the UNESCO Paris in the Caribbean. And the project has now concluded, and you can actually access the results on this link here, which will be in our recording. But basically, we are looking exactly at what is the immediate aftermath of the disruptions to educational infrastructures in the aftermath of an earthquake and a flooding, and how can we shorten the number of days that the education is interrupted by preventative measures, mainly by better retrofitting of the school facilities. And very interestingly, in several areas has been said that actually the peninsula of Wajima is a relatively less urbanized area and more provincial area with aging populations, and therefore less resources are being put into retrofitting buildings, and this would explain the widespread damage that we have seen in these that we have seen in this earthquake. And indeed, this approach is part of the talk, the issue of assessing building and preparing and increasing resilience. You will see that is quite an interesting part of the conversation that we will have today with the colleagues from Thornton Tomasetti. Just before I pass the words to Ruchika, just to say that we have symposium that we will run on 8 and 9 February over 2 days on recent advancement and the way forward in confined masonry construction practice, with speakers from a wide range of walk of life and a wide part of the world, from Latin America to extreme South Asia. Has been a bit of a nightmare to find a time that is good for everybody, but we look forward to see you between 1 o'clock and 4 o'clock UK time during those 2 days. And with this, and without further ado, I will pass the words to our colleague from Thornton Tomasetti, first Ruchika Kahu, Forensic Associate Principal, and David Ojola, also Forensic Associate Principal. We will then hear from Julie Piersrat, Principal of Sustainability and Resilience Practice Leader, and finally from Francisco Galvis. Thank you very much all for joining us, and thank you, Ruchika, for taking the microphone forward. And I will stop sharing so as to give everybody.
All right, thank you. Thank you so much, Dina. Let me share my screen so we can get started. All right, hope you all can see my screen.
Yes,
yes, we can.
Please.
Okay. All right. Well, thank you all for joining. Thank you, Dina and Raphael, for having us here. We are from Thornton Tomasetti. We'll each get a chance to introduce ourselves. So today we're presenting on from post-earthquake forensic investigation to recovery-based design. This is a topic that we all have investigated and taken part in personally. So I'm gonna start talking about our firm first, Thornton Tomasetti. So Thornton Tomasetti is a 1,500 person firm with engineers, architects, scientists, and other professionals. We have worked in 150 countries. We have offices, we have 45 plus offices in every major city of the United States and internationally. Our offices are spread throughout the world as shown on the map here, and they happen to be, some of them happen to be in close to the high seismic hazard areas. We also have offices in UK, technically 7 offices. Our 2 main offices are in London and Farrington, and then 1 in Warrington. Our firm is involved in a lot of different things. We provide engineering solutions, and we pride ourselves in solving problems and providing scientific and engineering solutions. As a firm, we work on a wide variety of markets. Here's the list of markets we work on: acoustics, critical facility, culture and community. Part of our firm designs tall buildings and stadiums. Part of our firm restores historic structures. What a few of us focuses on forensic engineering. So we've highlighted 3 solutions on here, which is insurance, resilience, and restoration. And these are the 3 areas we'll be touching on our presentation. I personally have worked in the insurance market for quite a bit. So a quick introduction about myself. As Dina mentioned, I'm Ruchika Kaur. I'm an associate principal in Thornton Tomasetti. I'm based in San Francisco. I have 15 plus years of experience. I started my career performing structural design of new buildings for education, healthcare, and government sectors. Then I spent more than 2 years in New Zealand assessing earthquake damaged buildings. That was mostly in support of insurance claims. I've also performed seismic assessments in Chile and Mexico, and also worked on litigation support for construction defects in standard of care. Now, what is forensic engineering? Each firm defines it slightly differently. This is how we as a firm have defined it for ourselves. So any problem that doesn't have a clear path to solution is a forensics problem. It encompasses different variety of jobs. Here is the list of it, and I'm going to touch base on some of this in the next slide. So the classic forensic engineering is failure investigations. So we're investigating the cause of failure or other performance problems that occur in materials, structures, or assembly by applying engineering principles. And when we are doing failure investigations, there are two main questions we're answering. First, why did the failure occur? Second, what and who are responsible for it? Typically, our work product is a report where we're presenting and explaining our findings. And our clients vary from government entities to designers, owners, manufacturers, attorneys, insurers, and contractors. There's a whole gamut of clients. For doing these failure investigations, a lot of times we do quite extensive document reviews. We're sorting through thousands of documents to understand what happened and reconstruct the facts and the timeline. Another example of somewhat a failure investigation is emergency response and stabilization. So anytime after a disaster or failure, we come to site and stabilize the structure. We define that as this area. I'm going to show a video of a telescope collapse, a Arecibo Observatory telescope collapse in Puerto Rico. I'm not sure if you guys are aware of this, but this happened, I think, a few years now ago. This is a single dish radio telescope in Puerto Rico, and it actually was featured in one of the James Bond films, so it's somewhat famous. This telescope weighs about 900 tons, and it's a 305-meter wide. So initially, when we were engaged on this project, we were asked that only one cable had failed. So we were asked to look at the cable that had failed. And during our investigation, a second cable failed. At that point, we started doing calculations for the loads for the other cables and determined that if no repairs were done, this satellite dish or this telescope could not hold the load any longer, and it would eventually collapse. On the day of the collapse, we actually had a drone inspection, and we also have a video of that.
Rushika, if you can speak slightly closer to the microphone, because for some audience is not so clear.
Oh, okay. I can talk louder. Thank you.
Yes, thank you.
So this is showing the failure at the cable socket. So we served as the engineer of record and provided an investigation, forensic analysis, and repair recommendations for this failure. We also determined the cause of the collapse and oversaw the demolition for this site. Another part of her firm does advanced analysis. It's essentially using scientific approaches to solve more complex problems that go beyond the usual. We're using structural mechanics and experimental mechanics to do this. We're using linear and nonlinear analysis to characterize the static and dynamic behavior of structural systems. So here are some images of our analysis results. The image on the left is showing the rebar where they were lap spliced, and the force transfer between the reinforcement and the congested area can be tricky, and we are capturing that with nonlinear analysis. The image on the middle is an incident of column settlement. This is a project in New York, and there was slab cracking due to no grout under base plate during construction. We modeled that, and our analysis captured the crack mechanism pretty well. The last image on the right is showing our nonlinear flat slab analysis and compares our predicted cracks to the experimental data, which matches pretty well. I have another video, and this is an example of controlled demolition. This was a partial collapse at Hard Rock Hotel in New Orleans, Louisiana, I think about 2 years ago again now. Our team responded when the structure was unstable. So the structure during construction was unstable, and also there were 2 cranes on top of the building that were left dangling. So our team came up with a plan and used explosives to bring the cranes down. One of the major goals we had was to protect the adjacent buildings. So when we decided to use explosives to bring down the crane, we did models and analysis, and the results aligned well with our expectations, and we were able to protect the adjacent buildings from further damage. Quickly, another thing I want to mention, part of a practice also does performance-based fire engineering. Just like we design for earthquakes and winds, we also design for fire. And in the code, there is a prescriptive design that uses component response and not necessarily the system response. It doesn't test connections or effect of restraint on axial forces or buckling. When we are doing the performance-based design engineering, we're using realistic spires and understanding realistic structural response. And in the end, this analysis is helping create a more resilient and safer structure. We also do post-loss investigation. So after a disaster such as a hurricane, we do damage assessment and repair recommendations. So this image is showing an aerial view of a property we looked at after one of the hurricanes. And the elevation view on the right is showcasing the damages we identified. Here is a list of recent post-disaster investigations that we have responded as a collective group. I personally have responded to a few of them, like the Chile one in 2010, Christchurch, Kaikoura earthquake, also Florida, and I think Texas hurricanes. So I'm going to move on to second part, which is lessons from forensics projects. So this is based on my experience in Christchurch in New Zealand. I'm hoping this can showcase how recovery can happen after a disastrous earthquake. So Christchurch, New Zealand had 3 major seismic events within a year, and it's known as the Canterbury seismic sequence. The first seismic event was a 7.1 magnitude earthquake on September 4, 2010. The damage was relatively minor throughout the city or even the country. The second earthquake happened on February 22nd, 2011. And it was a magnitude 6.2 earthquake, but the epicenter was relatively close to Christchurch Central Business District, and it was a shallow earthquake. It was quite disastrous for the downtown or the CBD area. It caused extensive damage to the buildings and liquefaction to the surrounding neighborhoods. The peak ground acceleration reached 1.5 Gs horizontally and 2.2 Gs vertically. This acceleration response spectra exceeded the 2,500-year building design codes and estimates based on the New Zealand models. So this was much more than anybody had anticipated. There were about 40 million US dollar in losses, and there were 185 fatalities. And most of the fatalities occurred in one building that collapsed in the Central Business District area. So Thornton Tomasetti had a temporary office in New Zealand for about 10 years. We responded to the earthquake in 2010 and were there till 2020. It was extended due to another earthquake in Kaikoura, which we will talk about a bit later. During this period, I personally evaluated hundreds of buildings while I was there, but our firm evaluated thousands of buildings and provided retrofit designs for many. So here is an example of a recovery process for a building that was insured. So in New Zealand, majority of the properties, the buildings had insurance. And in some ways that led to a lot of disputes and delays. There was a particular phrase in the insurance policies which required the buildings to be reinstated substantially the same as when new. So that little phrase caused a lot of dispute between the owner expectations and what the insurance carrier were willing to pay for repair. So it was a 7-story commercial building in Christchurch, New Zealand, close to the Central Business District. It was designed in 1985. The gravity system was precast, pre-stressed beams and cast-in-place columns. The lateral system was an eccentric concrete shear wall, which is shown in the highlighted region, which is the 4 walls in the bottom of the page. And the foundation was bulk piles and tie beams and spread footings under the columns. So this type of construction was pretty standard in New Zealand. They used a lot of precast and pre-stressed members, and concrete was pretty widespread. So we were engaged in 2014. So just a reminder, the Christchurch disaster earthquake was in February 2011. So we were engaged in 2014 to assess the extent of earthquake damage, to provide repair strategies, report the building percent MBS, and provide any conceptual strengthening. So that percent MBS, what that means is MBS stands for New Building Standard. It was an assessment of an existing building with current building standards and code load forces. So what could the existing building withstand using the current loads? And that percentage was defined. So anything that was less than 33% MBS was considered earthquake prone and required strengthening for reinstatement of the building. So it was important for us to identify if this building was earthquake prone or not during our repair recommendations. So here's some of the damage we found during our investigation. We were on site for probably a couple of months. We removed certain finishes so we could see the structural systems. We found diagonal and horizontal cracks in shear walls, as shown in the image here. The lines are kind of drawn over because the cracks are really hard to see. We did find larger cracks on the ground floor. There were separations and cracks also in the slab. There were diagonal slab cracks around columns and shear walls. There was also some damaged connection of precast panel, which was the cladding system of the building. And then stairs. There was separation from cast in place landing of the stair to the precast concrete stairs. That was also quite common system that was used in New Zealand. Here's a summary of her damages and repairs. So in our opinion, we said there was slight to moderate damage to the lateral force resisting system. The cracks didn't indicate yielding of rebar. So that was a hot topic in New Zealand while the repairs were going on, if the rebar has yielded or not. And there was testing done to determine, and I don't necessarily want to go too much in detail about that. But eventually we concluded there wasn't a significant effect on performance of the building, except the coupling beams, which had a bit more extensive damage. And in general, the damage was repairable. The repairs consisted of doing epoxy injection for a majority of the cracks, replacing the coupling beams at lower floors, which we thought were extensively damaged, and then no sort of foundation repairs, because we didn't necessarily think there was any settlement that had occurred for this building. We ran an analysis and compared the building to the current design demands, and due to inadequate diaphragm strength, the building was determined to be earthquake prone. So then we had to propose some repairs to strengthen the diaphragm for this building. Now, I think this is the more interesting part in the recovery. So the earthquakes happened in 2010 and 2011, and we are on site about 3.5 years later, evaluating this building. So between those 3 years, there was a lot of work going on. And this is what was happening. So initially after the earthquake in May, June, until November of 2011, there were investigations done. So an engineer was engaged who did post-earthquake structural inspection work. There was geotechnical investigation done and a verticality and floor survey done. The geotechnical investigation proposed installation of steel screw piles to reduce the risk of liquefaction in future events. Even though this building hadn't settled, there was a risk of liquefaction that they wanted to prevent for future events. Then in May 2012, there was hardness testing of reinforcing steel done. So this was done to see if there was any yielding of the rebar or not. Then in August 2012, a Royal Commission report came in. And the reason for this it mattered is because it was opining on performance of eccentric shear core walls, which essentially said it was an undesirable system and it led to a undesirable response of flexural torsional response. And it could initiate shear failures in the core walls. And the first engineer who was on site did an earthquake resisting analysis and came up with a building capacity. In November 2012, there was another survey came and did a floor level assessment. Then March of 2013, another damage evaluation was done. So this was the second engineer that had been brought to do this. In December 2013, then a third engineer was brought in to do a post-damage evaluation. And then April 2014, a fourth engineer did a desktop review. And then August 2014, we were the fifth engineer who came in and did the earthquake damage evaluation. So each engineer that was engaged was typically engaged by a different party. So the first engineer was likely engaged by the owner. The second and third were also engaged by the owner, and then fourth and fifth were engaged by the insurance company. So there was several rounds of evaluation for this building to even get to a resolution. So we finally issued a report in 2014 and provided a repairs discussion in 2015. Ultimately, it was decided that the repairs, the building would be repaired, and the repairs started in 2019, and the modifications were completed in 2023. Some of the issues that were debated and why this went from initial inspection in 2015 to work beginning in 2019 was, the first was concrete shear walls. In our opinion, we recommended that you could epoxy inject the cracks. But the other side, which would be the owner side, believed that the strength and stiffness of the wall could not be restored fully, which is how the policy had responded. Our argument to that was the potential loss strain capacity was very minimal. Since we saw more widespread and narrow cracks, that was an indication that the ductility demand was spread throughout, and there wasn't necessarily a local amplification of reinforcement plastic strain. The second dispute was coupling beams. We had recommended to replace coupling beams at lower floors. The owner engineer had recommended to replace the coupling beams for all the floors. Again, it was just the extent of damage. In their opinion, even small cracks, because of small cracks, they believed it needed to be replaced to maintain the strength and stiffness as if it was a new building. And then lastly, foundation. We have recommended no repairs for foundation since there was no damage. The floor was essentially leveled. We did a verticality study on this and did not find that there was any of the building was twisted. We also did intrusive foundation investigation, and we looked at the base of the shear wall and top of the foundation and didn't find any cracks, separations, any sign that there was movement. But the other side proposed a whole new foundation system, which was installing steel screw piles. And this design was more prevention of settlement for future events than reinstating or repairing the damage. And the way insurance policies respond is they do not pay for any betterment or improvement to structure. Their goal is to replace the structure in like-kind quality. So even though it would be better for a structure to prevent it from future settlement or issues, insurance company doesn't necessarily cover that because it is not in their best interest. Here is what the building looked like. Pre-modifications and after modification, as you're looking at it, there were precast panels on the exterior face of the building. There were some damaged connections, but ultimately it could be repaired. But this building was given a little uplift. I think part of the issue was concrete was looked upon as not the best system. And the city around it looked new, which had a lot of glass cladding systems. So they gave it a new cladding system to make it look more fresh and the perception that it was a new building. So my second case study is a little simpler than that. So you can have that one extreme that I just went over. So it took over 12 years to even for even an earthquake, a repair strategy to be agreed with, few more years into litigation, and then finally you're looking at a repair. So this one was also a building in the central business district that I looked at. It was a 14-story hotel, and it had a 3-story podium adjacent to it that was seismically separated. It was built in the same era as the previous one in 1986. It also had a precast interior concrete beams and columns. The lateral system was cast in place perimeter concrete moment frames. This building had a bit more extensive damage than the previous one. The concrete moment frames had vertical and diagonal cracks. The columns also had diagonal and horizontal cracks at top and bottom. We found floor slabs that had separated. So the floor system in this building was a precast T beams with a 16mm topping slab. So in a lot of locations, we saw separation or cracking in the topping slab. This image right here is showing a vertical offset and a large separation in corner of the building. As I was mentioning, precast stairs were quite common also in these buildings. So in this particular building, one of the stairs, the entire run of the stairs dropped. The connection at the landing pulled out. And the remaining stairs that were still there had quite extensive cracking. There were lift core walls, elevator core walls on the that had extensive damage at the top floors. There was a lot of falling and cracking. In this particular building, we did find the top 3 stories had a lot more damage than the lower floors. Part of the study, we did the verticality survey, and there was no pattern in the horizontal offset movement. We also did a floor survey, and we found there was a perceptible and measurable slope towards the middle section of the floor, and it was worse on the top stories than the lower floors. And this could be attributed to shortening of lift core walls caused by the structural damage. We didn't find any damage in the basement or at the lower floors that was indicated that the foundation had failed. So part of this exercise was understanding the extent of damage in the entire building. So when we were looking at this hotel, everything is covered in finishes. So we had to estimate the extent of damage from the limited finishes we removed. So here's the extent that we estimated. For tower building, we estimated 30 to 50% structural damage. For the podium building, there was less damage, so about 10 to 20%. And similarly for non-structural, we created percents. We also did a study to determine the MBS, which is what percent was this building earthquake prone or not. Our initial findings were that this building was not earthquake prone. It was about 40% of new building standard. We provided repair schemes, which included epoxy injection of beams, replacing moment frame beams that were extensively cracked, removing and replacing the entire topping slab, and then new concrete columns and walls on the top 3 floors. So we were just removing the top 3 floors and replacing them. And all the stairs were being replaced as well. So based on that, a cost estimating exercise was done, and these were the results for it. So the cost estimate came up for the tower building, the 14-story building, that it would cost about $36 million to repair the scope that I just described. And there's a little asterisk to it because there are risks, what we consider risk items that are not fully defined, which included there could be additional moment frame replacement that we weren't able to see. There could be additional diaphragm cracks that we weren't able to see. Same thing with beam cracking. There could also be requirement of structural upgrade because we only did an initial assessment which showed 40%, not as comfortable as we like. So we put a dollar value to that risk items and came up with another $2.75 million. So that bumped up the potential repair cost to be $39.75. And the replacement cost for this tower was about $40.7 million. So in this case, the replacement repair was relatively close. In most cases, the owner would decide to replace the building rather than repairing it. The podium was a different story. The repair cost was under $1 million and the replacement cost was about $8 million. So over there, you would be repairing it rather than replacing it. So after this study, so we were on site soon after, so we were on site soon after the earthquakes. Earthquakes happened in September 2010 to June 2011. We were on site from June to September 2011, issued a report, and ultimately the decision was made that the building would be demolished. So the owner got about, give or take, $40 million to repair or rebuild the buildings. The owner decided that not to rebuild the building. To this day, the site is empty. So here's an image of what the building looks like. The 14-story hotel back in, well, this image from 2017, but in 2011. And the site was demoed, I think, around 2013, or the building was demoed in 2013. And here is where the building would stood. I just want you to note the surroundings. So if you look at the Christchurch originally had a lot of brick infill construction as well, and a lot of concrete construction, which you can see from here and here. As of today, latest image we have, nothing has been rebuilt in sight. This is 10 plus years later, and the surrounding sites look quite different. As I was saying, that recent construction, the rebuilding in Christchurch, they're using a lot more steel and glass, which wasn't what was used 20, 30 years ago. So this is what the recent view looks like of this street in the central business district of Christchurch. These examples that I just showed are just showing how recovery has taken place in a developed country, you know, where majority of the buildings were insured. The first case showed that there was dispute that lasted over a decade, and eventually the building was repaired and given a facelift. Second case, which is this one right here, is there's minimal dispute and an investigation that finished within 6 months after the disaster. But there has been, this lot has been empty for 10 plus years, and as far as we know, there's no plans of rebuilding anything. So the recovery can be delayed, or there may not be any recovery or rebuild in some cases. All right, we are at a Q&A portion.
Yes, please, if anybody has questions, please either raise your hand or put a question in the chat or in the Q&A section. At the moment, we don't have any there is one in the Q&A. So it's Shmuel Yerushalmi. Hello, Shmuel. Happy New Year to you. What need to be a role of authorities in recovering building and places damaged in earthquakes?
Authorities do play a big role in recovery of buildings. So this requirement of earthquake-prone buildings and not repairing a building that's earthquake-prone and required strengthening was a requirement by Christchurch Building Authority, Christchurch City Council. Initially there was the Christchurch City Council came in and said any building that was less than 67% of MBS should be strengthened. So that meant hundreds and hundreds of buildings. And that led to a lot of delay because a retrofit cost was significantly higher. And the insurance companies weren't willing to necessarily just pay for retrofit. That's a new policy or new ruling that was put out after the earthquake. So there was a lot of back and forth. Actually, there was a lot of litigation over that. And eventually, I think it was agreed upon 34%, essentially, not an earthquake-prone building. If it's earthquake-prone building, strengthen it to make it above 34% MBS. That's all the requirement, and that was put forward by the Christchurch City Council. We've seen that happen also in other parts of the world. I know Mexico also released after Mexico City earthquake in 2017, also had requirements of what they wanted to do, as in, I can't remember that on top of my head right now, but they also required that if the building had certain level of damage, they would be required to retrofit the building. So those are the type of requirements that the state or the city established typically after the earthquake. I see, I know Francisco wants to pitch in.
Thank you very much, Ruchika. Very clear answer. I have just a follow-up comment, and then I think maybe we can pass the mic to David. You mentioned the case of New Zealand, where yes, the legislation basically required any building that had a capacity less than 1/3 of the capacity of a new build, equivalent new build, of course, would need, they were required to strengthen, but if they were 35%, then they wouldn't. And you said that your building was just about 40% the tower's capacity. There is clearly an issue there when you have let's say, privately owned and privately used building, then if it's a single house, maybe the resident decides to, yes, that 40% of the capacity or 33% of the capacity is fine. But when you have a commercial building, which is can be used also by let's say, relatively high density use, it's really a moral judgment of whether you are happy with that 40%, but also commercial, because it might be difficult to sell it over or to actually rent it out. So what part that had in the final decision to demolish?
So, I mean, for Christchurch in particularly, even to this day, the actual CBD looks quite different. A lot of buildings have been demolished for that reason. The building that we saw didn't necessarily settle, but a lot of buildings had settlement issues, and fixing that is a big undertaking. Even though the insurance company was putting forward the money for it, because they had to pay for repairing the building. A lot of owners decided to not necessarily rebuild in the same place. This particular owner decided not to rebuild at all. I'm not sure what they've done with their money, or if they've just left the market. What we're seeing that the Christchurch itself, the city is much more widespread. They don't have that the center anymore like they used to. They've created these little areas where they've rebuilt, and the rebuild is, I'd say, on a smaller scale. I didn't see a lot of tall buildings going up. So the owners, whoever decided to still stay in the market, have decided to go for smaller 2, 3, 4-story buildings rather than tall buildings that they originally had. So
the recovery is actually redevelopment or at an urban level, whether it was guided by the city or whether it was, just the owners and the almost an organic decision.
Right.
Okay. Yeah, and Dina, our next example will actually touch on exactly a case of that too, where
yes,
that factored into some of the decision making as well.
Please, David, go ahead.
Sure.
Yeah.
Cool. Well, Ruchika, I think if you stop sharing, I can pop in. Awesome.
And please, everybody, keep asking questions.
Okay, I think we should be all there. Great. So we'll pick up from there. Thank you, Ruchika. And what I'll be talking a little bit about here is one more example from New Zealand. I guess I'll start with the introduction of myself. My name is David Ojala. I'm an associate principal in our San Francisco forensics group, along with Ruchika. I do focus my attention on investigations and emergency response, standard of care investigations in particular. But I remain actively involved with risk and resilience consulting work and seismic retrofit, peer review, and other kind of proactive consulting. Like Ruchika, I started my career in design and then moved full-time into forensics. And when I joined TT in 2016, my goal, one of the things I wanted to accomplish being here, was to be in a place where I could take all these lessons that I was learning from investigations and apply them to design projects other proactive consulting type of work. And, TT's been a great place for that. But I will say that when I joined in 2016, instead of settling into my new office, getting to know my new coworkers, the Kaikoura earthquake hit in New Zealand. And I was voluntold to get on an airplane and move to New Zealand for a little while to go look at some buildings. And it turned out to be a really formative experience for me. I was, decently into my career at that time. But there were a lot of things that came out of this that impacted, I think, the way I approach my work moving forward. And I want to share one example of that with you. So I have a few details on the screen here about the two earthquakes that occurred after the Christchurch earthquake or Canterbury earthquake sequence, and affected the North Island a little bit more and helped them get into the action. So there were a couple of quick earthquakes that happened in about 2013 that impacted the North Island, the Wellington area. And then finally, the bigger one that occurred in 2016, the Kaikoura earthquake. Due to the kind of directionality of that quake, due to the distance, the frequency content of the earthquake at that distance, soft soil sites around the waterfront in Wellington, and what also happened to correspond with the natural frequencies of a lot of these concrete moment frame buildings in that area, the area got hit pretty hard. Now, Wellington was known, unlike Christchurch, which hadn't really been planning for earthquakes, Wellington was known to be a high seismic area. And so the buildings were ostensibly kind of designed to accommodate that. But this was really some of the first major tests of all these lessons that were supposed to have been learned in terms of recovery protocols and design after the Canterbury earthquake sequence. But as we'll see, the results were mixed, I would say, through that process. So the building that I want to talk about here is the Bank of New Zealand headquarters in Wellington. I was in the weeds on this one, technically speaking. I have plenty I could say on that topic. We'll speak to that. We'll look at a few photos. A lot of the sort of behavioral things we saw are the same ones that Ruchika talked about. She gave you a lot of the technical details, and I'm not going to do that again. What I want to kind of do with this case study is, and what was fascinating to me is how this building and how this project kind of played out publicly. It was major news in what was, by kind of global standards, kind of a small city. And so we're going to tell the story through news headlines that we pulled off. Maybe not newspapers anymore, a lot of web news, but we're going to kind of tell the story that way. And before I dive into, I also want to say that my intent with presenting this case study is not to shame the engineers that were involved here. I've met them. They're good people, good engineers. Frankly, the engineer whose building suffered a partial collapse, which we'll show here, and was the subject of a government inquiry, was probably one of the sharpest engineers I met, kind of a preeminent engineer in the area, and also designed one of the more innovative and high-performing buildings I inspected there too. So I'm telling the story here because it was very meaningful to me, in part because I really think this could happen to any of us when an earthquake happens in our areas. And I think that's kind of the point I'm trying to make. But so the background of the building is this was occupied by Bank of New Zealand, BNZ, leased from Centreport Wellington, who had developed this property on some reclaimed land near the waterfront in Wellington. It was what we call a high mu, very high ductility precast concrete moment frame structure, glass curtain walls, interconnecting bridges. And TT performed inspections of the building, both following those 2013 earthquake sequences, and then again in 2016, which is where I came along with dozens of other structures through the CBD. But it starts with this article, unfortunately titled, I think, "The Earthquake-Proof Building that is Uniquely Wellington in 2008." And I'm pretty sure that the earthquake-proof name or kind of claim did not necessarily originate with the engineer of record, but it certainly starts to set the tone for public expectation of what this brand new building was supposed to deliver to the public. And unfortunately, by the time we get to 2014, the building hasn't been open all that long. We come up with this headline: BNZ building faces a quake poser. And if you're an American like me, I had to Google this one. This was a poser. It's a particularly difficult question or puzzle. But after that 2013 earthquake, as you can see from this photo, very extensive non-structural damage. It occurred during off hours, but this is something that really could have been pretty hazardous. Relatively lightweight, hung ceiling finishes and things, but there's still a lot of ductwork, a lot of cable trays that came down. And this article from 2014, about 9 months after the earthquake had occurred, says the building is still not completed. Some people have moved back into certain areas, but water pipes burst, the building was flooded. And so it was really just this non-structural damage that knocked this building out of commission for such an extended period of time. So already we're at a spot where the public, the occupants, were relatively upset with how this supposedly earthquake-proof building had performed. And we move ahead to 2016, after the Kaikoura earthquake. This one shows up. BNZ building damaged in 2013 quake appears extensively damaged. And there's no photos that showed up here, but really what we're saying is engineers are still unable to access the building and get in to do their inspections. When we eventually did, here's the sort of conditions we were seeing. Not necessarily as severe as we saw in some of the photos that Ruchika shared, but still some engagement of the concrete frame, cracking of the precast concrete floors, and some definite engagement of the ductility of this building. Although, no partial collapses, nothing like that to speak of. About a year later, and this is, kind of diving in as we got more and more involved, this article pops up. Centerport sees BNZ and the Statistics New Zealand buildings empty until at least 2020, right? So this is already 2017, and at this point, they're projecting that these buildings aren't going to be occupied for another 2.5 years or so. Statistics building is what's actually shown in the couple photos I popped up here. This is the one building that showed a partial collapse. This building, this photo on the bottom is one that I took of a precast panel, a double T system that had fallen into a conference room. And this was of concern because had this been during business hours, there probably could have been some fatalities involved with this collapse. So BNZ was not at this level, but it was certainly kind of looped into that in terms of these examples of failures of the built environment after the quake. A little bit later in 2017, another kind of global article talking about the lack of performance, continued issues and safety issues. And this article goes on to highlight a lot of buildings that remained closed, remained in dispute, and were unoccupied at the time. So, this one, 10 November 2017, a year on, the building still lies empty with little sign of activity, but the story remains the same. The building's owners cannot say whether it will ever be repaired. It's up in the air because we're still working with our insurers with respect to the claim, is what the finance director says. Finally, about a year after that, for October 2018, it's declared that a settlement has occurred. This is where kind of TT's work on the building started to wrap up. And after 2 years after it was closed due to earthquake damage, the landmark former BNZ building on the waterfront is coming down. Centerport, which also suffered extensive damage to its port infrastructure, has confirmed it will not be building another commercial property on the site. And so that seemed to be kind of the end of this one. Again, another 2-year process before this was resolved, back and forth with a lot of debate between engineers, insurance companies, and owners and tenants, frankly. But, and at the end of the day, a building that we'll kind of talk about, may have been repairable, was brought down, and a major centerpiece of what was supposed to be the new modern downtown for the city remained barricaded, and ultimately it was demolished. But that wasn't quite the end of it. I mean, things continued, and in a country like New Zealand that, as I found, isn't really that litigious, things got a little feisty in the news after that point. So the building comes down, and then claims start to show up about why did the building do so badly. So this article appears, engineer claims that Wellington City Council ignored seismic warnings on BNZ buildings. And this came up from what was the original kind of peer reviewer for the building, saying that in 2006, they had some concerns. They were essentially dismissed, and the building was granted a consent, or i.e. building permit, 2 weeks afterward. maybe stemming from those accusations, some lawsuits start to spring up as well. So in May 2021, a little more recently, BNZ sues Wellington City Council for $101 million. Kind of interesting because it was a tenant rather than an owner of the building. So I think that became kind of a legal issue as to whether that was allowable or not. And then, a few months later, the insurer, Vero, said that they were considering a claim against Wellington City Council as well for, again, potentially negligence in having this building permitted to be constructed at all. And so that kind of wraps up at least the latest on where things settled. But this is what the public was seeing, right? And I knew some of this was going on in the background, but the point is that it didn't take a technical expert immersed in the details to see what was happening. And maybe the fact that there wasn't a lot of nuance either that was present in the presentation was one of the tricky pieces of all this. So from my opinion, while there were some flaws in the design of this building, I would say it was aggressive. The building was probably generally met the intent of code at the time. It stayed up, intended yielding mechanisms occurred, the building didn't collapse, the drifts were relatively small, at least the residual drifts. After some of the non-structural retrofits were made in 2014, I will say the non-structural performance improved pretty greatly, though there was some. It's my opinion, similar to kind of what we said in the past, that the structural damage was feasible to repair, but it's often through kind of limited replacement, epoxy injection, wrapping, and things like that. If there is some yielding of rebar, it is very difficult to restore 100% of the pre-loss stiffness and ductility. And that's probably something that's continually a challenge with any concrete building. We have these embedded elements that take that do the energy dissipation that are really hard to access and fix and repair. But that said, I mean, I think by many standards, if insurance weren't playing a role in this, it would have been deemed feasible to repair. Given the measured level of shaking that they had, I think the building performed roughly as the engineer and the code intended, but clearly not as the owner and occupants expected. So why was this building razed rather than repaired, along with a lot of others like it in Wellington and Christchurch? And there's a number of factors that play into it. It's never just a single-sided piece. Some of the factors I think that went into that decision to demolish it were that the designer and contractor, I think, really had the inability and or unwillingness to trust their own designs and what they designed for, and challenges assessing the performance of the building and how it had done, how it had actually performed, whether that's the amount of yielding, how to interpret the amount of drift that the building had gone through, a little bit of uncertainty in that. And that affected their ability to kind of confidently vouch for the future performance of the building. Essentially that question is, can it handle another one? And if they can't confidently say, yes, it can do that, that's going to hurt public trust and owner trust. We did see changes in the commercial real estate market dynamics in that area. That area, the city hadn't been blowing up the way that they thought it was when it was originally designed. It was a little bit further from the city center, and it just wasn't a popular place to be anymore. So there was a loss of market value associated both with that piece of it, as well as just the fact that it was damaged. And this was all playing out in the news. I think the inability to restore that full original strength to get the building back substantially as when new, as the insurance policy was written, impacted things. Is that reasonable if the owner is self-insured? I would maybe make the argument that if there were no insurance promising to put this thing back as when new, then an owner would have gladly done the epoxy injection and wrapped it, and it would have performed pretty dang well. But as a commercially insured property, I don't think that was going to fly. So insurance played a big part in this too, and the loss of trust from both the current tenants at the time and the general public, which are the potential future tenants that were sitting there watching this unfold. And to that last point, one of the moments that I think stuck with me the most from my time in Wellington was when I checked into an Airbnb that I was staying at, and I met the hostess, and she had her young daughter there, maybe 5, 6 years old or something like that. And when I mentioned that I was a structural engineer, the girl immediately said, so you're here to help us tear these buildings down. And I was really kind of flustered by that response. I was not expecting it at all. I assured her that I was really hoping to do the opposite. but that really bothered me that her young mind, in her young mind, that was my primary job, was not to build great things and help things stand up and build great communities. It was to tear things down. The thing is, I knew that she wasn't alone in that sentiment, right? It really spoke to the fact that that's how the public felt, and seeing and kind of being witness to that public distrust of a profession in that way was really tough. And that level of trust is hard to win back. And I think we see it now, perhaps in the change in the construction methods that we're using, and the fact that, say, in Christchurch, some of these buildings just aren't back anymore. And people are maybe moving and deciding to live in other places and occupy other structure types. So I wanted to touch on that other point, though, of insurance, which is kind of this thing that's been hanging over a lot of the stories that Ruchika and I were telling here. And as just a quick example of how this applies, Marquis and co-authors wrote a really excellent paper. I've got this, kind of citation here, and I'd really recommend reading it, on the complex world of the post-earthquake decision-making in Christchurch following the CES. And while he didn't go into insurance in as much detail as I maybe would have liked, and I'm, looking to help contribute to the literature on that point, one of the things he points out is that in New Zealand, approximately 80% of the losses in Christchurch were covered by insurance. And that level of penetration of the market is way higher than Japan, Europe, and other places where, even at a high end, 20% or so is about what we're looking at. And so the fact that there's that high penetration of insurance, some of the particulars of the policy language, meant that insurance really played a huge role in that earthquake recovery in Christchurch and Wellington. And it's unclear if it would play the same level of a role in, say, the United States, in California, when we have our next big earthquake here. There's a couple of common phases that I see in terms of owner and landlord response related to their insurance, or potentially their lack thereof, that happen in these events. The first phase often is hurry, clean up, get those occupants back into the building as soon as possible, especially if they don't have business interruption coverage, if that's minimal, or if the lease terms allow a tenant to terminate their lease if the facilities are unusable. So there's this very quick clean up, patch up the walls, maybe get a little bit of shoring in there, and then put out that public message that everything's all good. Phase two kind of springs in, especially once the occupants may be unwilling to return or the lease is terminated. There's that attempt to slow down the recovery and really maximize the value of the property loss claim that is going to be generated out of it. And that phase two is where a lot of things in Christchurch wound up, a lot of buildings in Wellington wound up. And it's where what we call ex post moral hazard starts to occur. And it's kind of where resilience dies in the recovery world. So quickly, what is moral hazard? In insurance, it's kind of a change in the expected behavior of the insured once you're covered by against a particular hazard or loss. Ex ante moral hazard is essentially before earthquake insurance, before an event occurs. Because I have insurance, I'm now going to engage in risky behavior. And that cartoon on the bottom is kind of along those lines. Spill all you want. It's a rented tuxedo. I got the insurance on it. And then ex post moral hazard is because I have paid for this insurance, an event happens, I'm going to get every dollar I can out of my investment by making claims. And so those two types of insurance, I think, or moral hazard, are really what put insurance at odds with resilience. And that insurance has the ability to disincentivize healthy, pro-resilience decision-making before and after disasters strike. Health and auto insurance have kind of dialed in things to help address those moral hazards. We have co-pays, we have high deductibles, we have certain premium levels. Property and cat insurance, I don't think, has found that sweet spot yet. And the message from insurers, as much as resilience has become really just a key phrase out there, is that it's a key factor in community resilience. And I think it is, but probably not in the same way that they claim it's going to be. It provides a very important infusion of money into the post-disaster world that's critical, but the kind of hurdles to accessing the money, I think, can lead to behaviors that can put the community and the individual assured's needs at odds with what the community needs as a whole, right? And so some of what we've seen through reconnaissance in the past is that underinsured communities often have the right attitude, right? They know nobody's coming to help. They know there's not just going to be a magical pot of money coming in. And so there's this kind of pick yourself up by your bootstraps attitude, shore up that building, patch it up, open the store. Nobody's coming to help. We got to get back to business. The heavily insured communities have that money post loss, but because of these moral hazard issues, they may be underprepared, right, to address it in the first place, and then doesn't incentivize the owners to act in the best interest of the community, right? So there's nothing that kind of tells the owner of that grocery store, hey, I don't care if you're trying to get a little bit more money out of your insurance. The community needs you to be open right now. And there isn't a mechanism to help drive those pro-community and pro-resilience sort of behaviors. So, I think that the topic needs some rethinking in the industry. It is a critical element in building communities, but I think some restructuring is necessary, looking into some different insurance products that might be more impactful, parametric insurance. A colleague of mine who works at Jumpstart Insurance gives kind of quick $10,000, $20,000 payouts to people based on level of shaking to help them address some of their immediate needs. That may be something that helps resilience without kind of hindering and waiting for large payouts. And the fact that what we're seeing these days as the level of natural hazards increase through the country, through the world, is that insurers are pulling back. That the market is hardening. It's harder to get insurance, and it's hard to just say, hey, I got insurance, so don't worry about it. I've addressed my risks. And in that world, there's a possibility where those investments in hardening your structure, resilient retrofitting, may offer better returns on investment than they have in the past. So yeah, those are a few of those thoughts. Obviously, it's a topic for another time. But that combined with some of these prior claims was a lot of the lessons that I think pulled out of New Zealand. And as we got back to things, started to inform the way we wanted to approach our work at TT in terms of proactive consulting moving forward.
Thank you very much, David, for this very interesting reading of the post-earthquake recovery. Clearly, you have put on the table quite a number of elements, but there are a couple of questions which I think they are slightly more related to the previous presentation. I will go through them, and I will ask Ruchika also to come back and answer if she can. So the first question is from Satwant Rihal of California Polytechnic, and he was asking about how the historic building performs during the Christchurch earthquake. And we all know of the cathedral that was substantially damaged, but I'm sure you have a much broader overview of how it all panned out.
In general, historic buildings, I'll say didn't do terrible, right? They were still standing when we were there. Definitely for the brick buildings, the parapets had fallen down, which is, first things we expect. But a lot of the brick buildings had been reinforced with, it was concrete columns with brick infill. In some cases, we saw essentially the entire facade or the elevation had fallen down, or the brick infill had fallen down. But overall, given what rest of the city looked like, the historic things did not terribly, in my opinion. There was definitely damage to them as expected.
Thank you.
The one fatalities that I mentioned, I don't know the statistics, but it was majority of them were from a one building that collapsed. So even though there were other hazards and stuff, it didn't. Ultimately, we're trying to save life, right? That's one of the main goals with buildings. So saying that rest of the buildings performed well, as in there was life safety, collapse prevention.
Yes, I seem to remember that there was an extensive campaign of retrofitting in the early 2000s in New Zealand relating to unreinforced masonry building with the insertion of ties if they were double leaf walls, and insertion and tie back of walls to floor structures and roof structures whether they were of timber or other material, but also this strong setback at regular spacing, so to break basically the free span of inflections of walls, both horizontally and vertically. So yes, I think some of that work certainly proved to be efficient, at least in limiting the damage, if not preventing it totally. Yes, and okay, Satwant, thanks you for the answers, and we have another question from John Lawrence Tuhala. I have observed that the duration of the investigation can take some time. As you have seen, it's several years. In the case of condominium or condos showing signs of cracks after an earthquake, how long should the investigation be, considering that the owners would want to know if they can or cannot return to their homes?
So
Well,
go ahead, David.
go ahead, Rich. You got to take a
Yes,
take a
yes.
stab.
I think you both touched
Yeah.
on this, so I think it's worth a double answer here. Yes.
Yeah, I'll let David expand on it. But typically, you know, after a disaster, there's a state of emergency here in the United States, at least, and same is true in other countries as well. And the buildings are inspected and tagged. So that's done relatively quickly. But that doesn't necessarily mean you can occupy the building, right? If there's 3 tags, I'm not sure if you guys are familiar with, you know, the green tag, all is good, you can occupy the building. Yellow tag, there is some damage, and yellow tag covers a really broad range. That could mean you can go in the building to get your belongings and come out, or you can occupy most of the buildings but can't use this entrance. So it can vary what that means. And then red tag, obviously, do not enter, can't occupy the building. And in terms of how quickly they can or cannot return, that I think depends on the city, the government, the resources they have. There isn't that one answer. I know the government, the city officials do prioritize homes, and they have emergency response teams that David is part of, and then let him expand to it, respond to homes first, and they do commercial property.
Yeah, I mean, I think
to
I was gonna say, I mean, I think to the time frame, sometimes it is really challenging. There's a number of things that can kind of impact the speed, and I kind of breeze through that. How can we speed up the insurance sort of claim process? Frankly, there's probably not enough engineers to inspect all the buildings in most locations, and that was part of the challenge of New Zealand, right? There's only a handful of firms down there, and there's way more properties than they were able to kind of handle, I think, on their own, which is why firms like TT, essentially, and other international firms helped by providing some resources to assist with that. In San Francisco, we're going to need the same. So you need some folks coming out, you know, to kind of assist. But pre-screening properties, the more complex ones, understanding where the likely worst case weak links are going to be, so that you can readily go and inspect those, are important. Utilizing instrumentation are all things that can, I think, help speed up that process and get you to an answer relatively quickly. As is trying to get the insurance company to maybe agree on one firm to give the answer, and avoid that back and forth dispute, which is often what drives the prolonged kind of claims process. And it looks like Francisco is interested in maybe piping in, or maybe not.
Yes.
The second question here about how this would look in less developed context is a really good question, right? I kind of hinted at that before. I mean, I think we will touch on a little bit in some of the future examples, but I think this is something that, to those of you out there who are doing some research, I think we need better data here, because in terms of how this looks, and how especially communities that don't have insurance or are less insured, what their recovery curves look like. I'm really curious to get better data at that, and to look at that a little bit more closely, frankly. I think we may have a few token examples that Francisco will be getting to soon. But I think that is an area I frankly have a lot of interest in, and would like others to help out with.
Yes, I think there is one last question about whether insurance company rely just on building permit issued by council, or they have or they make their own checks, or they have their own expert doing the checks themselves before issuing an insurance.
Yeah, I think it kind of depends on, it can depend on the country and the location and the market. In a soft insurance market, people will sell insurance. Insurers will give insurance policies to
Yes.
anything essentially for the right price. More and more, there is a little bit more for the potentially riskier losses. There is a little bit more of a detailed look given to certain properties. But even then, there's only so much time you can spend digging in. A lot of these are based on kind of averages and thinking as an insurer portfolio wide about your losses rather than honing in on a lot of detail on a specific one. But that's sometimes these examples we're giving are the outliers essentially in a portfolio that are driving some of the bigger losses, and frankly maybe they could do for a bit more detail than most insurers have historically been doing in the past.
But for
So, yeah,
instance, you mentioned L'Aquila, and they are, well, I've been involved in some of the recovery process, and I know it a little bit. The earthquake was caused in 2009, and in Italy there is, as you have said, relatively little insurance cover. So if the earthquake is above a certain, in fact, whatever the level of the earthquake, it's basically the government pays for the reconstructions, and it's in charge of disbursing the money, and usually through the civil protection organized particular technical office that will oversee the assessment of the building, the shoring, then the consideration of the projects, the approval of the projects for the reconstruction or repair or strengthening, and the financing of it. But that notwithstanding, you would think that, well, it's all in the hands of basically one institution, so it should go ahead and start immediately after the event occurs. Yes, in order to reconstruct L'Aquila has taken now the best part of 14 years, and it's not complete yet. So yes, we are in a situation where actually, even when you have completely different processes, they do not necessarily recovery. It's a long road, definitely. But my queries is more like, there are international organizations such as the International Finance organizations like the World Bank and other international banks that actually still promote insurance as the major element of, let's say, preparedness. And I wonder whether, some of the lessons learned have really registered in that respect.
Yeah.
I quickly just want to pitch in on the insurance bit. So just to give a brief response to that, most insurance companies are not going to the properties, don't look at the properties they're insuring. They look at a piece of paper describing the property, the age, the square footage, some basic information, and they have their internal risk models, depending if they're looking at one property portfolios, and then coming up if they want to insure the building or not, or what percent they would like to insure it. So there isn't a huge due diligence that is done from the insurance companies before insuring a property, generally.
Right.
Thank you very much, Ruchika. And I think, well, there is another question, but we can answer it later. I would like to now move on with the next presentation, the consequences of life safety. Please.
Yeah, certainly. Yeah, so I was just going to flip through here because I'll get to Francisco real quick. We're probably preaching to the choir here a lot, but what you've seen is some examples of what this kind of modern life safety approach to design is getting us, and what it looks like in practice. ASC 7 gives minimum design loads and associated criteria for buildings. And again, the target here is just life safety at that design basis earthquake, collapse prevention in that rare kind of biblical MCE event for at least a risk category 2 building. And for existing buildings, right, we accept an even lower tier of performance for that in terms of retrofit and the standard we need to kind of hit. But it's focusing on safety, and it really doesn't touch on functional recovery, the need to reoccupy, and repairability, with all of which we see came forward in the case studies that we put forward so far. And so, one of the things we found here in our proactive consulting work moving forward is that clear, real examples help, because it's convincing owners to move on from this bare minimum and do a little bit more that is really at the crux of what a lot of us want to do. We want to encourage that next tier of behavior. And it takes a lot. I mean, both making the economic argument, but also sometimes delivering things home in different ways. And we've found that having these examples help, and using our personal experiences from these events help. So from a non-structural performance thing, here's some examples of what we touched on. Napa was an earthquake that occurred close to us in San Francisco. We all love wine. Images like this are just catastrophic, right? And not just because we hate to see some good wine go to waste, but also because this is the business, this is the economy of that area, right? And so there's actually been a lot of work that's gone into appropriately anchoring wine barrels and those sorts of facilities after earthquakes that have happened there. Here's some examples we touched on from New Zealand, both in terms of the non-structural performance, taking a building out of commission. And this photo on the side too, which is from a building that structurally performed pretty dang well, but these precast floor panels, it's hard to see, used to be oriented in this sort of direction, right? So they've given out, and the occupants of the building had to be evacuated through the windows because their egress routes were not accessible. Anchorage, same sort of story. We have one more good oscillation, and this heater probably would have come down in the middle of this warehouse and taken out some of the storage racks along with it. MEP lines failed. Here's an example that has actually been very effective for me lately. These are two offices on the same floor of the same building, just across the hall from each other. The building structurally performed very well. The difference is that they were built out by different firms using very different methods. So this one on the left, poorly braced, hung ceilings went, fractured a sprinkler line, and flooded the building. And if it hadn't been for that, the office across the way would have been perfectly fine and able to continue its operation right away. But it's not just isolated to earthquakes. Here's some examples of it taking, essentially several months after a hurricane to address kind of storm surge related flooding issues from a Hurricane Ian work we did in Florida recently. And then even winter storms. Here's where my search and rescue team went out this past winter and went to the Mammoth Lakes area in California. Obviously, tons and tons and tons of snow and no place to put it anymore at some point. And while obviously it led to roof failures and collapses and things like that, one of the issues is that all this snow piles up and can impact some of the utilities. So a lot of propane lines, either local tanks or local systems, are fed in the house by an external exposed pipe, comes up, makes a 90-degree bend, and goes into the house. All the weight of snow and ice and during the melting process can separate those lines, gas lines, from the building itself. The gas can then be allowed to leak through the building or through the snow, even tunneling its way into different areas. Somebody turns the lights on or somebody tries to light their stove, and there can be catastrophic explosions. And so we see a couple of examples of what that looked like here. So we don't think of non-structural hazards for winter storms either, but these sorts of things, if we're not thinking resiliently and the hazards that these events can pose to all aspects of our building, not just structural, we can be left pretty vulnerable for that as well. So here was supposed to be a checkpoint. We just had some questions. So I'll just let Francisco continue on through and pick up his end of the presentation and talk a bit more about some of the life safety issues here.
Super. Thanks, David. All right, let me get this going. There you go. All right. So now, can you all see my screen?
Yes.
Okay. Great. Cool. All right. Yeah. So I introduce myself first again. So I'm Francisco Galvis. I am a project engineer at Toronto Massetti in the San Francisco office. I sit in the forensics practice, but also work with the resilience practice. I'm kind of working in both. I started my career as also Ruchika and David in design, but of bridges in my case. In Colombia. I'm originally from Colombia. Started there working on bridges for a few years, and then moved to academia for my PhD. That's when I came to California in 2017, and now a couple of years ago, joined TT to work more on the forensics and resilience practice. All right, so through that experience in forensics, I had the opportunity to go a few months after the Turkey earthquake in February this past year in a reconnaissance mission that the firm conducted. So we went to the southeast of Turkey to witness what had happened there. As I'm sure all of you know, this was a really devastating earthquake sequence that claimed more than 50,000 people's lives and caused more than 80,000 building collapses. And there's a fair amount of other of interest on this devastating event and a lot of research and reconnaissance on the collapsed building. So we turn our eyes into what happened to the buildings that didn't collapse and that perform as they were supposed to perform, right? That they did the performance, the life safety, given that this event was pretty close and in some cases exceeded what the equivalent MCE would have been for the area. And I'm just bringing one of those examples that I think was striking to me when I saw it in the field. So this is in the city of Kahramanmaraş. That's on the northern side of the rupture. Where you see here, this is 38 residential 11-story towers that were built in 2014. The Turkey building code it's on par with the US and the most advanced building code. So they do have all the ductility and requirements that you will expect for modern earthquake design. Of course, designed with life safety as the performance target. These buildings use a bearing wall system. So a lot of walls, most of the walls that serve as partitions are also structural walls with a few brick walls as non-structural components to partition some of the missing walls that are not load bearing. And then the result when we went there, like 10 weeks after the event, is that all of this sort of complex would be demolished, right? They were already vacated, and you can estimate, thousands of people not having where to stay. And the result of that being large tent camps everywhere else where we looked around. So we went closer to one of these buildings and tried to understand what drove that demolition decision. And there's a lot of the points that David and Ruchika touched earlier in their New Zealand examples come up here again, but now without the insurance situation here. And I think this also addresses one of the questions that, what would happen if the insurance penetration is not as high? And maybe this is one of those case examples. So in this case, this building had some exterior damage. You can clearly notice which buildings were reinforced concrete structural walls and which ones, which part of the building was just brick walls where had severe damage, but still not residual drift that will be like immediately concerning. Then we went inside the building and tried to look for structural damage that will definitely indicate that, we should get out. And we didn't find anything that would be structurally really concerning, right? We did find, of course, the structural elements engaged, right? So you see some of the coping beams having some cracking and stuff like that. You also see some damage on the walls around the elevator. You start seeing maybe the cold joint not handled pretty well, but nothing that would indicate, well, this is in immediate, at the verge of collapse or anything like that. However, walking through this building and looking at the non-structural damage, right, the feeling you get, especially if you're not an engineer, it's way different, right? So you see all of these cracks everywhere else and a lot of damage on the non-structural components that are scary, right? So the damage to infill walls, and this is like have been said many times, was a major predominant issue. Have these rigid partitions that are not well isolated from the structure, and that scares everybody, right? And then what happens is that, this past month, these demolitions are already underway, right? So it kind of really make us pause and think, these buildings didn't do anything different than they were supposed to do, right? They moved, they dissipated energy, they didn't collapse, they allowed people to evacuate. So from the eyes of the building code, they are kind of a success, But is it really a success for the community and for all of those around? We estimated around 7,000 people who lived in this, fairly new building or neighborhood, are displaced, and who knows when they're going to be able to go back and have a proper place to live. So that's, I think, would be one of the things to consider when we think about the consequence of life safety. Now, not only when the smaller events that affect mostly non-structural components, but also the larger events that also create structural damage and other consequences. So I think the message here is that building codes are meant to prevent collapse only, and that's something that doesn't really register with everybody. We engineers know, but we also are responsible to communicate it well, and especially those making decisions, either private investors or public entities, to really know and understand what are the consequences of this, and these examples can really show it. As David mentioned, and Ruchika, of course, the non-structural damage is the main driver of losses in most cases. And there is a huge portion of loss that comes from, not from damage, but from business interruption, right? And from all of the consequences of not being able to use a building after an event happened. And that's something that needs to be considered in the decision-making of anybody thinking about developing a project. So that's sort of what the example we had on Turkey. And then with that, I want to sort of give the mic to Julie, that will now walk us through other type of events, now a hurricane, and then how that kind of resulted into our resilience consulting practice. So Julie.
Yes, just a second, considering you have a checkpoint and considering there is questions that relate to resilience. So between reinforced concrete and steel structural system, which one you consider more resilient? And the question is from John Lawrence Twala again.
Oh, good, thanks. Yeah. That is an interesting question, and my answer is, and my opinion in general, and others please chime in, is that any system can be resilient, and it depends on how it's engineered. We just need to understand every system has its own advantages and disadvantages, and that is part of what we should consider where the design is being done on. And so there is no preferable, in my opinion, right? It's just that some have different, let's say, disadvantages and advantages than the other, and there are other factors to consider as well. And any system can be made resilient by fairly little amount of money, and that's something we'll touch on later in the seminar.
Yeah, very, very diplomatic, Francisco. I think inspectability and repairability is kind of the key. Steel sometimes has that advantage. It has historically had that advantage, but there are still ways to do that with concrete construction. And so I think that's kind of the key factor in what makes a structural system more resilient compared to the actual building material itself.
Thank you both very much. And Julie Piesrat, please, the microphone is yours.
Great. Thank you so much. Thanks, Ruchika, David, and Francisco for setting the stage. Francisco just mentioned Hurricane Sandy, which occurred in the Northeast US. And this was another forensics job that, we responded to at Thornton Tomasetti after the fact. Which sets the stage for resilience. And so my name's Julie Petrak, and I lead our sustainability and resilience practice at Thornton Tomasetti. The resilience practice was born out of this event that you're seeing on the screen here. So I joined after this resilience practice was originated, but my background is in civil and geotechnical engineering, and I've been doing resilience work for much of my career. I worked on the West Coast of the US for many years doing geotechnical engineering and seismic resilience for dams and levees and things of that nature, water conveyance tunnels. Of course, at that time in my career, we never really called it resilience. We were incorporating sea level rise into levee design and seismic redundancy into tunnel design, but it was more about redundancy and recovery. following an event. It really was Hurricane Sandy that occurred that sort of brought the terminology of resilience into our lexicon and helped us move forward into this path of being a little bit more proactive of how to prepare before an event occurs so that we can bounce back quicker in the future. So I've been with Thornton Tomasetti now for 4 years, and I think, you know, now we're seeing kind of what David alluded to earlier versus resilience versus insurance, and how we have clients that really want to prepare beforehand and kind of avoid these losses with preparation. So so you can see here the difference of the Manhattan shoreline. That 1650 yellow shoreline was the original outline of Manhattan Island. And, you know, of course, we went through and filled in much of this land where you can see the green line showing the 2013 outline. And then there is the World Trade Center site located to give some proximity of where we are looking. The very interesting thing about this is when you look at the Hurricane Sandy inundation map, it looks very similar. The amount of land that was flooded during Hurricane Sandy of Manhattan looks very similar to the inundation map, looks very similar to this historic map. So we recognize that, you know, we've filled in land, but here you can see the inundation map and how that relates to that 1650 outline with different depths shown here from FEMA flood maps. This was a underpass that goes into the Battery Tunnel in downtown Manhattan. This was a Thornton Tomasetti job that we went afterwards to look at the damages that had occurred here at the Battery Park underpass. You can see the level of water was at a 3.83 meter height and nearly to the top of the clearance of this tunnel. And then this is another location in Lower Manhattan where you exit the subway if you're going to take the ferry over to Staten Island. This is the South Ferry subway station. Clearly inundation all the way from that lower platform subway up to street level. And so these were kinds of the, you know, the images that we were seeing and kind of the recovery that occurred after this hurricane. And here's a video showing the rushing water in this location and just the magnitude of damage that occurred. So after a lot of reconnaissance following earthquakes, we use these same techniques to respond to this event after this hurricane. So I mentioned already, basically following this hurricane, we decided, you know, what can we do to be more proactive, help our clients prepare and adapt to these changing weather conditions in the future, rather than always being responsive and having to rely on insurance for recovery. So that was kind of the birth of this resilience practice within Thornton Tomasetti. So we define resilience as the ability to prepare, endure, adapt, and thrive in a disruptive and changing world. And I think that changing world piece is really the key here. We recognize that, you know, our sustainability practice, the side of the practice there, you know, we're working on reducing greenhouse gas emissions in all of the projects that we are working on. But we know that the greenhouse gas emissions that are occurring today are going to be still contributing to tomorrow's extreme weather. And so we recognize that in this changing world and the future uncertainties that will occur, we want to be able to communicate these risks to our clients so that we can prepare and endure these in the future. So I mentioned uncertainties. You can see that through manufacturing, transportation, and our buildings, we are emitting a lot of operational and also embodied carbon through our development and human activities, which is then contributing to these greenhouse gas emission scenarios that you see in the lower left-hand corner. The interesting thing here is that because of future uncertainties and also not sure of, you know, what will happen tomorrow, what direction society will go in, there are a lot of different scenarios that may occur. So you see with the red line here, that's a lower emission scenario pathway. If we were to really curb emissions over the next short-term duration of 10 to 15 years, you know, we might be able to change things further out in the future. But then if you go all the way up to this black line with your highest emissions scenario pathway, RCP 8.5, that's really an extreme scenario where, you know, we are business as usual, or things can perhaps even be getting worse. And so here's kind of the range of uncertainties that we look at over the short, medium, and long term with our clients to determine like what really should be the design criteria moving forward for a project. When you look at that, how that translates to different shocks and stresses on the right, we look at climate hazards. We also look at earth hazards. We recognize that earthquakes are really not affected by climate change. However, there are effects of climate change that may impact earthquake damage, and that could be rising sea levels and how they affect tsunami waves, also rising sea levels and how they affect groundwater tables and where liquefaction might occur. So that's something we look at holistically. You can see all these other climate hazards that we look at, including drought and wildfire, stormwater, pluvial, flooding, groundwater changes, obviously extreme heat and high winds, tornadoes, and then coastal flooding and sea level rise. And this is just representative of how we look at a problem when we are starting a project, of really identifying all of the relevant climate shocks and hazards that could occur in this location, and then how those might change over time. And then again, what those variations and changes into the future might be like. So we take a very holistic approach to resilience. I mentioned my background is in civil and geotechnical. I'm joined by my colleagues with structural backgrounds as well. The team is multidisciplinary. So we have environmental engineers, we have architects, landscape architects, scientists, research and development folks. And that really helps us take this holistic approach where it's a very iterative process. So when we start a project, we are starting in this diagnostic phase where we want to look at, you know, what's happening at the specific site that I kind of just mentioned with these different shocks and stresses. And then moving into the strategize phase where we take a multidisciplinary approach to integrate a resilience strategy into a building design. Once that's being implemented into the design and construction, we're really looking for operational resilience of this building. And it's always a conversation with the owner and also the operations and maintenance personnel, which brings us to this monitor, manage, and improve phase. So depending on the dynamic nature of clients' challenges, you know, we're constantly having a review, learning, and innovating our solutions to sometimes even revisit the diagnostic stage to make sure that we're coming up with the best solution for the owner, who ultimately, once the designer, you know, we as the designer walk away from a project, we're empowering the owner to understand the resilience strategies that we're incorporating into the building design, both structurally and non-structurally. So I mentioned, you know, we start out looking at all these different hazard levels. The really important thing is we know that the code, as Francisco mentioned, you know, it provides a level of life safety, absolutely. And we know that the code is going to prevent structural collapse. But we don't know beyond that if there are operational resilience wants and needs from the client, you know, what that looks like. And we also know that the code is based on past events and occurrences. So we consider those lessons from the past, but we also want to stay focused on the future. And if you're looking to the past, that's really taking a prescriptive design mindset. So when you're taking a prescriptive design mindset, you're looking at the historical data and past events. You're assuming that that's going to provide acceptable performance for life safety, but you're not clear on, you know, what could occur if something beyond code level occurs. Which is why we want to take more of a resilience design mindset where, yes, we're looking at what's happened in the past and how that impacts current hazard levels, but we really want to stay focused on the future and what those future climate projections look like. That's going to build for better performance by minimizing potential repair costs and business disruption. And then, you know, we're also looking at taking a risk-informed, but client-specific and future-focused approach. And I think that client-specific piece is really the most important. We can have two projects that look like they might be identical, but what ends up happening is into the future, those projects may look completely different depending on clients' needs and wants. So we know that climate risks are increasing in both intensity and frequency, and these changes happen differently all across the globe. Here we are showing a US-centric map, but we can see what's happening with FEMA estimates in terms of flooding during a major storm compared to an independent researcher's map of a storm event and what that looks like. And we can see that independent research is showing that the percentage of properties at risk of flooding during a major storm is much higher than what the FEMA estimate is. And a lot of that has to do with bureaucracy and policy changes that take just a very long time to occur and to adopt over time. And so it's really important for us to look at the latest climate science to understand what's happening in the future. So I want to give a couple case examples of how we're applying this to projects. Francisco will talk a little bit more about seismic redundancy and performance-based design for seismic activity, but I'm going to focus a little bit on this flooding scenario, kind of coming out of what we learned from Hurricane Sandy. An interesting concept was Sandy was a coastal flood event, and so when we look to the future to see what the preparation is for that type of event, you really have a long warning period. However, in the US and across the world, within the UK, we've been seeing a lot of heavy precipitation events. These are much different. You have very little warning time to prepare for these. And so what's shown here is this New York Hall of Science project, which is located in Queens, New York. This was flooded due to stormwater from Hurricane Ida. So this was a different phenomena than what we saw with Hurricane Sandy, where Hurricane Sandy had a very, very large coastal storm surge, but very little rainfall, less than 1 inch of rainfall occurred during that storm. Whereas in Ida, it was a lot of heavy rain and no coastal storm surge at all. But this project, we looked at where the inundation occurred to the project site, and then what could be done from a short, medium, and long-term mitigation plan. So as part of this project, the other interesting thing about inland flooding and precipitation flooding is with coastal flooding, we have, in the US, we have FEMA maps, and elsewhere there are coastal flood maps that can be used to determine what your base flood elevation should be. And then you can use the code to add a level of freeboard on top of that to determine what your design flood elevation should be for a current storm. And then often we incorporate sea level rise into that design flood elevation so that we are looking to the future. However, when we're looking at precipitation flooding, inland precipitation flooding in particular, you don't often have inundation maps to use. And so through our practice, we have developed GIS mapping analyses to look at hydrological analysis at a watershed level to determine depths of water for future precipitation. So what you can see here on the bottom left is a schematic section of this New York Hall of Science site, how the water is flowing in, what the flood elevation looked like, where these low points might be, and how we can get that on-site water off-site and what those elevations should look like. So in the small table, I know it's a little bit difficult to read, but you can see we also looked at different comparisons from what the citywide standard is for development, which is a peak intensity of 1.75 inches per hour, and how that compares to what we saw during Ida, which was nearly triple at 3.15 inches per hour. So the current 100-year 24-hour rainfall event is 2.88. So you can already see that that 3.15 that we saw in Ida is above the current 100-year 24-hour rainfall event that's being, that's in the code level. So we took that data, incorporated future climate change data to look at the future and see what would that 2080 scenario look like for the same event. And we are getting a 4-inch inches per hour intensity for rainfall, which is quite intense. And that is what the input that was used for what you're seeing on the right, these two maps on the upper right. We looked at the entire watershed of what was draining to this New York Hall of Science. So the blue areas are showing the different subcatchments areas. It's almost like looking at a river where you have different river tributaries that are contributing to the larger river. The red area outlines the site subcatchment, and really you can see there's just a lot of water that's going to this site. When you go to the bottom right-hand corner, we then looked at using that 4 inches per hour of rainfall intensity applied to the topography of the site and the hydrological soil conditions. We developed this estimated floodable area map using open data and identifying different depths of water so we could understand how high will this water be at the site locally based on these future rainfall events, and with that height, what protections need to be made for the museum. So on the left-hand side is the short-term strategy that we came up with for New York Hall of Science. This is showing a flood wall. It was a deployable wall that now sits there semi-permanently while the long-term strategy is further developed. This wall has already been tested now 3 or 4 times for rainfall events, and it's worked wonderfully. So you haven't had the inundation into the museum that they had in the past. While we work on the long-term strategy, we take a 3-layer approach when it comes to flood resilience, both from stormwater and coastal flooding. So you can see in the yellow, our first layer of defense is a site strategy. So we want to look at how we can manage water at the site, divert water away from entrances, divert water away from the site altogether, perhaps some natural nature-based solutions like berms and vegetated buffers. But then we know that if that gets breached, we want to look at layer 2, which is in the orange, and that's at the building perimeter, where you might be using deployable flood barriers, measures that are at the perimeter, waterproofing techniques, perhaps flood-resistant glazing and things like that. And then for particular critical utility rooms or critical operational rooms within the building, we move to a layer 3, providing some interior compartmentalization of those interior critical rooms, where we will fortify those rooms or hopefully elevate those rooms out of the floodplain over time. Now, these strategies obviously take a lot longer to implement. So this is and it's also something that can then be adapted upon as we develop better climate science moving into the future. So we always start kind of with the short term, low-hanging fruit to help our clients, immediately, while we work out this long-term strategy over the next year or so. This is another project that occurred coming out of Superstorm Sandy. So this was coastal flooding related. NYU Langone Health is a large hospital complex on the east side of Manhattan. We've been involved with them immediately following Hurricane Sandy. During Hurricane Sandy, their emergency generators that were providing the backup power, because the municipal power source was flooded, and so the hospital would have been out of power. It was running on the backup generators when those were also flooded, and so then the hospital lost power. So since then, we've been working with them for over a decade to develop this campus-wide flood mitigation plan. So we've been doing that now since 2013. It includes 10 different interconnected buildings. So these are all existing buildings, some dating back to, mid-century. To date, I think actually this number could be updated. We've provided over 130 deployable flood barriers. One of them is shown here on the screen. This is a flip-up floodgate. So when this is in its nested position, it sits down into the ground, trucks can drive over it, it's completely imperceptible, and this can be raised in 2 different methods. One is with a buoyancy, where as the waters rise, it automatically lifts the barrier. And the second way that this can be lifted is by mechanical means, where someone can go press a button, and this is hydraulically activated to lift into this deployed position. I mentioned we take this monitor, manage, and improve phase very seriously. That includes, as we have resilience strategies that are implemented and constructed at a building, we take our forensics lessons learned and go out and provide boots on the grounds inspections. So what you're seeing here was an actual bathtub test that we performed on this barrier to be sure that under flooding conditions like what we would expect to see and what this was designed for, taking future climate change into account, that this barrier works the way it was supposed to, and that it was installed correctly, while also empowering the hospital staff who will be operating and maintaining this into the future and providing annual inspections and things of that nature to be understand all of the moving pieces and be empowered to, you know, operate this on their own in the future. So you can see we had a lot of different Thornton Tomasetti disciplines involved here, including our forensics team, our renewal team who works with retrofits of existing buildings, our kinetics team that specializes in movable structures, and then also our transportation team, which includes our site and civil engineers. This is another building located at the NYU campus, the Smilow Research Institute. This was another building that was damaged. It holds much of the research for the hospital, and one of the more difficult things to achieve here was, if you look on the upper photos on the upper left, this is a ventilation system for the electricity generation for the building. So these are where the vaults are located for all of the electrical capacity for this building. And then on the right-hand side, you see another ventilation fan vent that is required for ventilation of that machinery. So we started this building retrofit in 2017 and recognized that none of the flood resilience manufacturers that were on the market had a product that would work for either of these scenarios. And so what I think the really interesting photo is on the bottom left. We worked alongside, you know, taking lessons learned from what's happened in the past and our investigation experience. We worked directly with a custom flood barrier manufacturer to come up with a custom flood barrier design here, which is shown on the bottom left, and then also on the bottom right, where we rebuilt part of the structure and have these vents that are now within that structural wall. On the left-hand side, what you're seeing on the bottom left, it's really essentially a shower curtain that is nested directly adjacent to those vents in a container. The container can be open. The shower curtain can be pulled across a cable, bolted into place on the opposite side, and then it hangs outwards so that it can withstand debris impact loads, and it can withstand your hydrostatic and hydrodynamic and wave impact loads, but then also provide the ventilation that's required during a flood event to have that electricity continually operate the facility. So I think I mentioned we've really taken a lot of lessons learned from forensics and what we've heard so far today. So these are just photos of, you know, areas that we've just been boots on the ground, taking those lessons learned while these resilient solutions are implemented. And particularly on the right-hand side, you can see from the previous photo, this flood barrier shower curtain that's now in its deployed position, and another bathtub test we were performing here, and a hose test, excuse me, a hose test as well, that was then checking all of the joints of where the connections were involved. And this performed very well, and you know, this is a really successful project to date for us. So I mentioned, you know, in general, we've taken lessons learned from what we've seen in the past. On the left-hand side, you know, I just wanted to take a little bit of a step back and a broader look, and we are definitely taking a multi-hazard approach to climate risk assessment. So it's all dependent on the project location. I mentioned we look at past events, but we know that those impact the current code, standards, and guidelines for current hazard levels. So it's really important to look at the future projections. But then because of the variation in future projections, it's important also to look at what the likelihood of these might be, and then potential impacts based on those likelihoods. So taking a more probabilistic approach. And then for certain clients like NYU Langone Health, where access to the site is extremely important, we can also look at potential area-wide impacts to come up with what the correct resilient solutions are for a specific project. At a grander scale, we've also taken this approach, which is really exciting, at a master plan level. So we can look at communities, from a municipality level to incorporate resilient solutions at a grander scale and really look at how we can make communities more resilient. So when we're looking at a master plan, we really identify some goals, and these are some consistent goals that we've developed that we look at when we are looking at resilience for an entire community. We really want to maximize co-benefits, so looking at promoting the ecosystem, the natural ecosystem and habitat that exists, and promoting biodiversity to increase public health. We also want to safeguard the infrastructure that is part of that community. So building in redundancy for energy, transportation and mobility, communications, and then of course, potable water and food systems. Certainly protecting property against damage and property loss, preventing interruptions to business operations. And then this also leads to promoting public safety during the event, and then also when, you know, we're having a recovery from event, and then overall enhancing the quality of life for the community. So typically when we're working on a master plan, we then can come up with different resilience strategies and design criteria for certain project typologies. So depending on where the project is located, whether that involves regional flood protection, waterfront revitalization, street infrastructure, or building design criteria, even land use planning and policy, and then considerations for emergency preparedness. And we come up with a toolkit that can be used then by this community in the future to build better. One example of this was a project that we completed last year in Paysandú, Uruguay. This was a community that had suffered historically from riverine flooding on a pretty regular scale. You can see different river levels that were investigated in the upper left-hand corner, and those lower and upper bounds, and then also, you know, what those look like in the future. And so we took a look at those future levels, and then on the right-hand side, looked at what that regional flood protection might look like in this area, with berms where those needed to be located versus where you had less space and needed to have an actual structural flood wall. And then also some floodable areas that were more wetland and how that could actually be incorporated and used as an opportunity. So I think the largest lesson learned on master plans, and really kind of going back to that monitor, manage, and improve phase of our resilience approach, is that there are many voices. It's incredibly important to get stakeholder engagement. If you're not empowering those end users to understand why you're doing something or to get buy-in, then, you know, you're not getting ownership within the community, and it's the most important thing that we do. So when we're talking about resilience strategies, we really take an eye to climate equity, environmental justice, making sure that every stakeholder is heard, that those considerations are taken into account, and it ultimately ends up promoting a more positive path forward for the project, and solutions that are implemented that, you know, many people feel accountable for and have ownership over. So I touched on this a little bit already, but essentially, you know, once we've decided to come up with a resilience strategy, what that might look like from a conceptual standpoint, implement that, and then construct it, we really work with our clients very closely to come up also with these emergency action plans. So whether that's at a community scale or a single existing building, we come up with these plans that have timelines to deployment or timelines of action. And this includes the context or trigger, like what could occur. In this case, this is a hurricane example. You have a forecast that a hurricane is coming. There's a 5-day countdown, and there's an understanding of what that key personnel looks like and what their logistical plan is for resource management, and then implementation and deployment of the mitigation efforts. And then we're also very clear on what that maintenance schedule is. So this is something that gets updated every year that we work a lot with certain clients on. So with that, we're at another checkpoint, and if there's any questions, I'd be happy to take those. Otherwise, I know we are, this has been a really great dialogue, and we've got a little bit of time left and a few more things to speak about, but thank you so much.
Yes, there is a very quick questions about Turkey, so maybe we can take it now. Francisco maybe can answer that. Was the single state ownership the whole complex, and therefore a major factor in condemning the whole rather than inspecting and assessing the block by block? The whole development was probably singly owned.
Yeah, I don't know about that. That's the Turkey one, right?
Yes.
Yeah, it's unclear to me if it was singly owned. We talked with a couple of the residents that were kind of, when you see engineers with helmets and vests, the community feels drawn to tell the story of how they experienced this disaster. And we had a conversation with a couple, and it sounded like it was there, like the units where like each unit had a different owner, like people bought those apartments. That's how it looked like, but I can't like, put a stamp on it.
Thank you very much, Francisco. Maybe we can progress with the next piece of this fascinating presentation. I'm just concerned that we are a little bit out of time, and people might need to leave. So yes, it's important.
Yeah. I know we got just like a bit over 15 minutes left, but
okay.
We
please
will,
go ahead.
All right. So yeah. So one of the things we've been working on, and I think this is kind of the wrap up of this seminar, will be the projects and the approach we're taking on what we're calling recovery-based design, which is one of the areas that the resilience consulting practice is growing on. So the concept, we have touched a lot on it already, is this idea that the code, it's aiming for a performance target that's somewhere in the safety area, but that it is possible to achieve better performance, right? Things like reoccupancy, functional recovery, of even full recovery, if that's what the risk appetite of an owner, it is what it leads them to. But to be able to get to those better performance, we need to quantify performance in specific metrics, right? And the way that shape out is where we try to answer a couple of questions. The first one is, what is the performance of a building, coming back to the case of earthquakes, given a specific earthquake scenario? How does specific design decisions impact that performance? And then we try to quantify that in three sort of verticals. The first one is the repairability of the structure, like how likely is for a structure to be repaired after a certain event, how much is the cost of repair, and then how long it will take to repair, not only to get back to reoccupied, but to be able, for the building to be able to offer their basic intended functions. And there are some metrics we can decide into how to measure each of these three verticals, all of them involving uncertainty, right? So we need to consider and communicate with the clients that this is no longer a passes or fails type of answer, a deterministic approach, but there is uncertainty, and that we can have a discussion to decide what is the level of uncertainty that they're happy or comfortable sitting with. And the way we've been doing this is using the state of practice or state of the art in this type of assessments. For earthquakes would be FEMA P58. So is using the performance-based earthquake engineering framework that has three main advantages, right? It's component by component, considers all the uncertainty in every aspect of the problem of the risk assessment, and provides these quantitative metrics, right? That would enable a conversation with a client that is usually not an engineer and not an expert in these topics and doesn't think of earthquakes all the time like we do. This method, in a nutshell, really has just 4 modules. Starts with quantifying the hazards. Then for that hazard, estimate the structural response to determine basically how much the structure moves. With that, probabilistically quantify the damage of the different components inside the building, and then aggregate all that damage to estimate decision variables, which are ultimately the metrics of performance, like repair costs, downtime, and repairability. The way that looks like for downtime or functional recovery time, it's basically simulations that what happens with the building after the event happened, and those are curves like this, or recovery curves, some I call them, that shows what happens at different points in time. And of course, probabilistically, there are multiple simulations of this, and shows how the building goes from this damaged state towards getting back into function again, if that is what happens, or if it's demolished, then what is the course after that. The key here, as Julie mentioned as well, is that the stakeholder engagement is critical, because we are now going beyond the code, right? We are now doing something that's above the minimum, so it's not prescriptive per se. So we need to understand what is that the stakeholder needs, what is their risk appetite, and ultimately try to define what are the limits of these performance metrics that align with their expectation, their needs, and of course, their budget. So that's really important to have a lot of conversations with them to define those metrics that will redefine the basis of design. So we have a couple case studies. Well, we had originally 3, but let's skip the first one and then touch the latest 2 where we put these concepts into practice. So let me just skip this one really quickly and then get to the second one. So this is an interesting one because this is a project in the northeast of the United States, academic facility. This project still going on that started with coastal flooding, right? So the resilience team got kind of in the project because the client was really concerned about flooding in this area, and they really want their building to be resilient all the way to the year 2100. Right, and that was the perceived most important hazard. So of course it is really important and is a dominant hazard at the site. And through different conversations, it was evident that this client was interested in using the most extreme projections for the design. Right, so when we realized that the risk appetite of this client was really a lot higher than a typical, let's say, project, well, we brought up the topic of seismic. We said, well, the northeast of the United States is not typically known for the big seismic hazard, but there is some hazard. As you can see in this map, is like intermediate, right, in that yellow area. So if the risk appetite of this client is that low, then it is, it's that high, then a better performance for seismic is something that they'll be interested in hearing about. So we move forward with a deeper study on what might be the response of this building. And there are 2 different earthquake scenarios, the design basis earthquake, but then also a more frequent service level earthquake that would be comparable to, let's say, the 100-year flood plus high tide. So that's what we did, and using all of these probabilistic methods to quantify this in terms of repair cost and functional recovery time. This is the results for repair costs on this building. In the service level earthquake, like let's say baseline design, this is all code minimum building that the structural team and all the other consultants had already put out in a schematic design phase. We took those drawings and did the analysis and estimate that for the surface level earthquake, this building will have negligible losses. And then for the design basis earthquake, we'll have somewhere about 3 to 3.5%, which is really a lot lower than what one would expect for a code-based building, showing that the building already has, on this baseline design, a better performance than average. Although that wasn't true for downtime, right? So for downtime, this figure shows in the horizontal axis the days after the earthquake, and in the vertical axis shows the probability of 80% of the building being not functional, right? So a high probability, it's bad, basically. So we have a really low chance of having most of the area of the building not functional for the service level earthquake, so that's really good. But if this design versus earthquake, a higher event that has about a 900-year return period occurs, then we are looking at something about 9 to 11 months on average of this building being not functional. And this really resonated with the client and something they are not willing to accept, thinking back to their risk appetite for flooding. So they asked us what they could do to improve this. So we dig deeper into our results of downtime to identify what are possible scenarios of recovery and what is getting damaged that's hindering the fast regain of function. And we identified that there were 4 main things that were doing that. The first one was damage to elevators. The second one was damage to the HVAC system, both having long lead times to get the equipment to replace what has been damaged. But then there were also some minor structural damage on ordinary braces, not ductile elements that are not customary for that area, and damage to pendant lighting that became falling hazards. So we aligned our resilience recommendations to tackle those 4 topics, right? Like say, consider seismically rated elevators rather than an ordinary elevator sort of system for that area. Brace the HVAC equipment for seismic loads or even higher, a little bit higher, using an impactance factor only for those type of equipment. Use bracing on the seismic, on the pendant lighting. and try to consider, instead of ordinary braces, higher ductility systems on this area. All of these things are things that are routinely done in California, but not in the Northeast, and that we think are important for improving the resilience of this project. But the way we presented this to the client is not like this is all you need to do, but more of a tier approach, right? Where we say, look, we have these 4 recommendations, but you can stack them and see how that relates to the additional cost, right? So the first thing that we say, this is, if you were just going to do one thing, focus on the elevators. If you're going to do 2 things, do elevators and HVAC. If you're going to do 3 things, then anchor the HVAC stronger. And then if you're going to do everything, then we do everything. And then we quantify how doing those, considering those recommendations will reduce the repair costs. So it starts from the 3.5 we showed before on the design basis earthquake to go down to about 1%. It was already low. This is not really that much of a benefit. The benefit comes on the functional recovery time, where we were looking at something like 10 months or so on the baseline case, and we can go all the way down to a few weeks, right? Of course, there's uncertainty and a lot of uncertainty around these metrics, but we can definitely show that you can go from about a year to a few weeks to a month of functional recovery time doing this, these 4 recommendations that, by the way, in this orange curve, we're showing the added cost of doing those recommendations, which for this case is somewhere about $1 million. And this project, for reference, has a total budget of $350 million. So we're talking about 0.3% additional construction cost for this amount of improved performance in terms of recovery. So this is something that really resonated and is in the higher phases of design, impacting how the project is moving forward. The final example we have here is it's a bit of a more recent case where the concern was earthquake from the very beginning. There's a public facility in the Caribbean that has seen recent seismic activity and a lot of damage to non-structural components. I mean, and non-ductile concrete building. So this is a non-ductile concrete building, existing building now. It's not a new design. So there's different challenges that arise from having an existing building. In this case, the building code, ASCE 41 already has 2 scenarios, 2E and 1E. We propose to have 1 additional scenario that we're calling the BSC 0E, which is a 30% chance in 50 years, a lot more frequent event, to estimate performance. In a nutshell, this is what the building code targets for existing buildings, right? So something around these lines, again, life safety. The stakeholder is really desiring something really good around the functional recovery for the stronger event and full recovery for the lower event. And what our analysis doing basic ASCE 41 deterministic risk assessments show us that the building it's way far from that expectation and also under the building code targets. So the reason why that's the case is, as you can expect, non-ductile concrete building built about 60s or 70s had a lot of issues with ductility detailing, with the proper location of lap splices and all that good detailing that wasn't done at the time. But the thing is that after doing those evaluations, the client, that those evaluations with ASCE 41 are really helpful to answer the question of, does the building need retrofit and what the scope of the retrofit? But this stakeholder had more questions. Specifically, they wanted to know if the building was safe compared to new building, or how safe was. They wanted a number on that safety. And they also wanted to know if tenants needed to evacuate and wait for the retrofit, which is something that's way out of the scope of what evaluations like ASCE 41 can do. But it's something that probabilistic risk assessments can answer. And that's what we did. So after a lot of work, this was our final sort of slide of result on this project, where we tried to show this client that, yes, the building is it has about 4 times higher probability of collapse than a new building if you plan to use it for 50 years. But if you plan to use it for 5 years, which is the scope or the time expected for the retrofit, the risk is a lot lower. Yes, it's higher than the new building, but it's lower than what you were already accepting on a new building planning to use it for 50 years. So it makes sense to stay in the building, wait for the retrofit, and then continue using it after solving the long-term problem. So that's what, and this is the state where this project is going. Of course, we also did some recovery simulations to estimate functional recovery time, and are in the works coming up with retrofit concepts that will address these long recovery times that you can see plateau at here at the higher levels, indicating demolition and reconstruction of the building as the most likely case scenario. So I think that concludes all of what we had to present today, going all the way from forensic engineering to our latest projects in recovery-based design.